last we met, I was talking about sound as a wave. And in that discussion, I said many times that sound waves are created by a vibration and that they carry energy through space. And the chief example, it's rather obvious to point out, is that here I stand in front of you speaking this physics out loud. The vibrations that I create in my vocal cords push and pull on the air. The vibration creates the wave. The wave transmits the energy, not the matter. The air from my lungs doesn't arrive at your ears. The traveling vibration that is the sound wave is what arrives and vibrates your eardrum and creates the sensation of sound. When you're lecturing about physics, that's a pretty obvious comparison to make. But here at the end of this particular unit of our study, I think it's kind of fun and interesting that we can talk scientifically about a thing that has been a passion of the human race since the very beginning, and that is music. There are sounds that are pleasing to human beings, and there are sounds that are not. An immediate distinction that I can make is, now that I understand that sound is a wave, and that waves have a wavelength, a speed, and a frequency, any sound wave that I encounter in nature is probably a combination of frequencies all together in a mush. If there are many, many frequencies in a sound, and there really is no mathematical relationship between them, they create what we call noise. Now here is a quite imaginary pressure graph. It shows the pressure as a function of position of a wave. It's like a snapshot of a wave. Every wave that I've shown you so far was very pretty, like the sines and cosines that you see in math class. This wave is a hot mess. And so when these pressures impinge upon your tympanic membrane, they vibrate it in a way that is unpleasing. And we have a word for that, and we call it noise. But if a sound wave that I encounter has within it few frequencies, just one would be lovely. Not surprisingly, if there's just one frequency, we call that pure. But if it's 1, 2, 3, 4 frequencies, and those frequencies have a good proportional relationship to each other, then you get a waveform that's sort of smooth like this. Now it has some kinks along the top, you can see, but in every cycle it repeats itself quite naturally, and it doesn't have very sharp changes in pressure as it goes along. This is what we call music. Now, across the globe, it differs what human beings find pleasing. And in fact, it sort of differs, the greatest differentiation is by hemisphere. We distinguish between Eastern and Western music. You can immediately tell music from the other side of the earth, because the chosen frequencies of those sounds are different from the sounds that were chosen in the West. Because we have in Western music what's known as the Western music scale. It's a set of notes that are played that have a particular mathematical relationship between them. And they're chosen in such a way as to be pleasing to the ear. Today, I'm going to talk about a specific note that I've mentioned before. Whenever I've been discussing frequency on the lead up to this, I've talked about the A note, which is 440 hertz. But here on my slide, I have 3 A notes labeled A2, A3, and A4. These notes are different frequencies. Where is my A4? A3, A2. There are 3 distinct frequencies for those, and I've listed them here. 110 hertz, 220 hertz, 440 hertz. My hope is that you immediately see the pattern. Each successive A on the scale is double the previous one. A2 is 110 hertz, twice that is 220, and then twice that is 440 hertz. The very last thing that we spoke about in our last meeting was the decibel scale of sound intensity, sound level. And what we learned is that the decibel scale is a log scale because every successive 10 decibels is a factor of 10 increase over the previous. Every 10 decibels is a factor of 10 increase. Well, here I have an A note, which is very cleverly followed by a B, a C, a D, an E, an F, a G, and then an A. There are 1, 2, 3, 4, 5, 6, 7, 8 steps, which is called an octave. Every octave is a frequency 2 times higher than the previous. 2 times higher, 2 times higher, 2 times higher. The decibel scale that we described was 10 times greater sound level, 10 times greater, 10 times greater. The decibel scale uses a log base 10. Now my equation said 10 times log the ratio of the intensities. When you just write log, it's assumed that the base of the log is base 10. But the Western music scale is log 2. When you learned about logs in math class, you probably learned about the natural log, which is a log that is specifically base E. So the base of the log scale of the Western music scale of notes is 2. Every octave doubles the frequency. The A is sometimes called the root, but it has a very pleasing multiplicative factor, which is why I mentioned it in the first place. Right in the middle of the piano scale is a note that we call middle C. That note has a frequency, it's called C4. It has a frequency of 261.63. This is why I talk about the A note. The A note has these easy frequencies to talk about. And so today's discussion is going to be mostly about the A because of the way those frequencies work out nice. The middle C, called C4, which is this key here on the piano. And it's called the middle C because on the staff of musical notes, it is the note that is between the bass clef and the treble clef, and there it is right there. 261.63 hertz is the frequency of the sound. I use frequencies of sound in physics, in science, but in music, we call it the pitch. So in any time in music-ese, musical conversations, that we make a reference to the pitch, we're talking about the note and its frequency. That's sort of the link between music and science. Many scientists are musicians and vice versa, but it's not necessarily true. You could be a brilliant musician without having any idea how any of the science works, and today's discussion is about sort of getting that organized. It has within it a few fun facts. For example, the human ear has limitations in sound level that we discussed. You can hear from 0 to 130 decibels of sound. Beneath 0 decibels, you just don't have the capacity to accumulate that nervous sensation to perceive the sound. And above 130, it's painful. Well, the same thing is true for pitch. Young humans can hear sounds from about 20 hertz to 20,000 hertz. The reason why I say this is as you age as a human being, that range starts to narrow and narrow and narrow. And in extreme old age, you hear a very narrow band of frequencies. It's a common observation that the elderly often have difficulty hearing the words that are spoken to them, and the reason why is that any notes that appear in language that have very high frequencies or very low frequencies can no longer be heard. And so it becomes difficult to discern the sounds that you hear. The pitch and the sound level are completely independent from each other, which means a note, like an A note on the keyboard, can be played at any volume, and it's still, that's a rather obvious statement, but can be played at any volume, and it's always an A note no matter what volume it's played at, because the pitch and the sound level are independent one from the other. Of great interest to me here is quality of the sound. When I say quality of musical sound, I don't mean, gosh, that sounds good, or that sounds bad. The chief interest is this. I think you are aware that the same note played on different instruments sounds different, despite the fact that it is the same frequency. I have this electric piano here. Gosh, I wish I had I feel weird saying a real piano. I think everybody knows that inside of a real acoustic piano, there are strings, just like the guitar strings. But when the keys are hit on the piano, for example, the key for the A, when that key is struck on the piano, a hammer hits the string. A piano also has a very different shape from a guitar. On the guitar, I have a string that is the A string, and I can pluck it. That's the A note on the guitar. Now, they don't sound the same. If I had you close your eyes and say, which one am I doing? Am I doing the piano or am I doing the guitar? You would have no trouble telling the difference between the two. And yet they're the same note, which implies that they're the same frequency. And I think that's super interesting. We don't just have one musical instrument for our enjoyment. We have many musical instruments that create sounds with varying physical attributes, like different ways of creating the vibration. This harmonica here can play an A, but it has no strings involved in that. I blow air into the holes, the air goes across some metal tabs that vibrate, and that vibration creates the sound that we hear. When I strike the guitar string, it's a very complicated thing. Sure, the guitar string vibrates, but the guitar string is connected to the body of the guitar, and as I play it, I can feel that the whole instrument is vibrating. Its shape, its size, the quality of the materials that the guitar is constructed from determine the quality of the sound that I get. But how do I define quality scientifically? Well, the idea is that when an instrument plays a note, it is never playing a single frequency. It's playing many frequencies of the same note. Remember, there are many A's. This one, this one, this one, this one, this one. There are many A's. And when I pluck my guitar string, there is one A that it is playing the loudest. But there are other A's in there at different loudnesses. Not specifically, not half, not double, not triple, not a third, not a fourth, nothing like that. Random loudnesses of all of the other A's. How this guitar chooses what A's it will play depends on the construction of the guitar, the materials that it's made out of. And this guitar that I have here is the guitar that I play. This is my guitar from home. I brought in my home guitar. It is a very high quality guitar. It's a Martin D18. Martin guitars, by the way, are manufactured in the state of Pennsylvania, and it's a short drive for you and your friends to get out to the Martin Guitar Factory and watch them building guitars. It is an incredible tour, and they have an amazing museum. I love this guitar. Don't think that I'm a super freak. It smells nice. It does. It does. It smells nice, and it sounds beautifully. I have another guitar here. This guitar is my work guitar. I think that everybody that plays music, and certainly there are people with us today who, as part of their thing, have an instrument that they've learned to play. Playing music can sort of bring some enjoyment to your life. And so I like to have a guitar at work. in case I feel like playing a little something just to relax if I get stressed or whatever. That guitar over there costs about $3,000. This guitar cost, I think, $130. It smells like Elmer's glue. It is a terrible, terrible piece of crap. It is made from poor materials, bad craftsmanship, not very carefully. I wish I had, is there a guitar player in here? I don't want to push this too far, but sounds the exact same. Well, that's the thing, if we could get playing both at once, then we would know. But it plays an A. If we were to analyze, I guess I could do it on the tuning stand, but it's not gonna, hang on. They're not the same. They're not the same. And I can tell you, aside from scientific instruments making careful measurements of the frequencies involved, I love this guitar, my home guitar, and I hate this thing. It's terrible, 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 terrible. And the reason why is that every instrument is constructed in such a way that it determines the number and loudness of the various waves that make up the sound. For example, these three notes here, this one's an A, this one's an A, this one's an A. They have names, not important right now, but let's call this the fundamental or the first harmonic. This is the second harmonic, the third harmonic. The actual note that you hear when these three notes are played simultaneously is primarily this one, because this one is the loudest. But sneaking in there are these others. And when these others sneak in with different loudness, you can see they both have a lower sound level because the amplitude is less. The note that I get when I add all of those together is an A, but it has a very special shape to it. You can tell musical instruments by playing a note and making this graph, and it's like a fingerprint for the musical instrument. Certainly, a good enough fingerprint to tell the difference between a high quality instrument and a low quality instrument. It's the combination that results in the sound that's distinct to the construction of the instrument. Now, before I move on from this particular idea, I also want to point out, and this is not so much a scientific point as a musical point. When creating music, you can certainly play single notes. There's probably someone out there who on the piano might be able to give us a very good rendition of Twinkle, Twinkle, Little Star by hitting single notes back and forth. But very often, many notes are put together to create what's known as a chord. For example, on the guitar, an A chord sounds particularly different when the same three notes are played on the piano. Oh shoot, I gotta come up with a A chord. Oop. A chord. A chord. So if the individual notes don't sound the same from one instrument to the other, the combinations get even further away, and the performance of a musical piece on the piano becomes distinctly different from the performance of a piece on the guitar. Different instruments produce sounds that are similar in general but different in the details. So here's a graph of what I'm talking about. In this case, it's a piano and a clarinet because this is obviously the image that I had available to me. But it could just as easily be piano and guitar. You can see that the pressure waves look very similar, but they are not exactly the same. The difference is the quality of the sound. Once again, quality does not mean good. Quality means the selection and loudness of the individual frequencies that make up a given note or tone. In a manner of speaking, Each recipe uses the same ingredients, but in different amounts. And if you were in your kitchen to, download a recipe off the internet and make that recipe according to the instructions, and then make it again, but change the amounts a bit, same ingredients, different amounts, you would get a result that tasted different, but hopefully was ultimately the same food of interest. Now, it is possible for one to study the specific physics of every kind of instrument that there is. I could divide instruments into 3 classes for this purpose. I could study the physics of percussion instruments. When you hit a drum, the head of the drum vibrates with a particular frequency. A lot of folks don't know, I think, that a drum kit needs to be tuned just like a guitar does. It's actually not uncommon for a drummer to not be aware of this. Whenever you go out to see live music and the kit isn't tuned properly, it can be very frustrating from a musician point of view. I could investigate the physics of wind instruments, like a clarinet or a flute, or for that matter, a harmonica. Instruments where air blowing through the instrument creates the vibration. But in order to keep us localized and focused, I'm going to choose to investigate my favorite instrument, this here guitar. Now, a guitar creates a vibration, everybody knows, by virtue of a string. In this case, on this guitar, 6 strings, most common. 6 strings supported between the bridge at the tail end here and the nut at the top of the neck. So there's a string simply suspended between 2 points. And that string can vibrate in particular ways. Before I get into discussing this diagram here, this fancy diagram, I have connected this elastic cord for demonstration purposes. I come all the way over here. And so I have this, it's made of rubber, in case you're curious about that. I have this rubber cord over there, and it's tied off at the pipe at the far end, and I have hold of this end, and I can cause it to vibrate. As a guitar player, I would use my finger or a guitar pick to pluck it, and then it begins to vibrate. The vibrations of a string are really waves bouncing back and forth of the string from one end to the other. But because the string is tied off at the far end and tied off at this end, there are only specific ways that it can vibrate. For example, this is the simplest vibration of this string. It's called the fundamental vibration or the first harmonic. But if I increase the frequency with which I agitate it, this is going to be, I don't even know how well this is going to work out for me, but if I increase the frequency, oh yeah, I can create the second harmonic. I will probably develop a massive cramp if I try to create the third harmonic. Each harmonic at a higher frequency, if I wiggle it fast enough, I might be able to get 3 loops and 4. I would go crazy doing that. These are the ways that a string can vibrate. The length of the support is here, and this first harmonic, it's going to take a little bit of imagination. I'll use my marker just to make it clear. This first harmonic is half of a wavelength. Because if I draw the full wavelength of a wave, I have to use some imagination and go off to the right this way to get the full wavelength. This harmonic is half of a wavelength, half of a full wavelength. The second harmonic, you can see, it does a full cycle, up and then down and then back again. The second harmonic represents a full cycle of the wave, and so that is a full wavelength. And I've noted there, full wavelength. For the third harmonic, I get a wave and then another half. That's 2 halves of a wave, and a half of a wave is 3 halves of a wavelength, fits on the string. And then 4 halves of a wavelength, which is 2 wavelengths, and so on and so on and so on, forever and ever, to higher and higher frequencies. Each frequency a full octave above the other. double in frequency. There's a pattern. And I've written the pattern here as a mathematical expression. The length of the instrument from support to support, and I've got a guitar which happens to have a length of 65 centimeters, but of course there's someone out there playing a little ukulele, right, that's got a short little length. And some of the lengths of the piano are enormous, and the piano all different lengths. But the length of this string is equal to n, where n is an integer, 1, 2, 3, 4, lambda over 2. N is an integer, and it's the harmonic number. Because if I put in n is equal to 1, it's lambda over 2, first harmonic. If I put n is equal to 2, it's 2 over 2 is lambda is the second harmonic. If I put in n is equal to 3, it's 3 over 2 lambda is the third harmonic, and so on and so on and so on. Each harmonic is an integer multiple of the length of the instrument itself. And so now I can write an equation for this. Because if the length of the instrument is an integer multiple of the wavelength divided by 2, I can solve for 1 over the wavelength. Just a little bit of algebra. I multiply 2 over here, and then, actually divide the lambda over to the left-hand side, and then divide the L over to the right-hand side. It's funny that I solved for 1 over lambda, but look what happens. Here again is my equation for the speed of a wave. The speed of a wave is its frequency times its wavelength. So if I solve this for 1 over wavelength, 1 over wavelength is frequency divided by speed. Frequency divided by speed. So if these are both equal to lambda, they're both equal to each other. And so the frequency of a vibrating string, which is what creates the sound in the musical instrument. The frequency of the string, the frequency is the note is the pitch, is equal to n over twice the length of the instrument times the speed. Well, that's great, and I love that I was able to create that little algebra there. But the thing is, I need to know the speed of waves on the string. Well, as it happens, I know a little something about that. All waves work this way. The speed of a wave is some kind of elastic property. Remember, in our discussion about sound waves, the medium should be elastic that the waves travel through, because the medium has to bounce back in order for the waves to travel easily. So the medium has to be elastic. The more elastic the medium, the faster you go. But also, the medium has inertia. The medium doesn't want to accelerate. The medium is sluggish. It doesn't want to move. So the medium has some inertia. Wave speeds are always the square root of an elastic property divided by an inertial property. In the case of a string specifically, where does the springiness of a guitar string comes from? It comes from the tightness. If I go back to my demonstration string here, my enormous demonstration string, if I do not pull tightly, the string is floppy as anything. You wouldn't even describe it as elastic. The way that I make this string elastic is by pulling it tight. Now it springs back. So the elastic property for a string is the tension in the string. The inertial property is the actual mass of the string. Now, this material that I'm using, this rubber, has a particular mass. There's nothing I can do about that. How much mass it has depends on its mass per unit length. This material, if I take a certain length of it, it has certain mass per length. And here I go with the Greek letters again. Mass per unit length is given the symbol mu. I know, I talked about mu before in the context of the coefficient of friction. But mu is the mass per unit length. And so now I have an equation for the frequency of a string on my guitar. Now, the reason why this matters to me is, what if a guitar doesn't exist? I want to build one. I want to build a guitar in such a way that I can tune the guitar to particular frequencies. But here's the deal with the guitar. My guitar is a certain size. The length of the strings is from here to here. And there's nothing I can do about that. Except I can. From time to time, particularly those of you who are not necessarily musically inclined, you've seen that a guitar player will take this gizmo that's called a capo and hook it onto the guitar and clamp it on there. The reason why we do that is because now I've shortened the length of the guitar. I have control of the length that appears in the equation by clamping down on the guitar like that. The reason why is when I shorten the length, you can see because the length is in the denominator. If I shorten the length, I'm making the denominator smaller, which means I'm making the numerator larger, which means the frequency is higher. So now my G chord is now brighter than it was before. Now, as a singer, I have limitations. So if I want to sing a song, I may have a hard time singing a song in a particular key. By shortening up the guitar and putting the capo on, I can shift all of the notes in such a way as to make it more compatible with my voice. But for all intents and purposes, I don't have any control of the length of the guitar. Also, the guitar has bronze strings on it, and I don't have any control over their mass. The only thing that I have control of is the tension in the string, which I control with the tuning machines. By turning the peg, I can tighten or loosen the string, and that's how I control the frequency. So just as an example problem to solve, I always want to do a little bit of an example before exiting the notes. Here's my equation for the frequency, and let's say I want to know how tight do I need to make the string on a guitar in order to produce a 440A frequency. Well, I'll assume that it's the fundamental. News for you, it's not. But I'll assume that it's the fundamental, n is equal to 1. So if I set n is equal to 1, don't worry, I did a bunch of algebra and I did it correctly. The tension in the string works out to 4, the length of the instrument squared, the frequency squared, the mass per unit length. 4 is 4. The distance from the nut to the bridge on this guitar is 65 centimeters, or 0.65 meters. The frequency I'm shooting for is 440 hertz, then squared, and the mass per unit length of the string, which I'll admit I had to look up, is about 4 grams per meter. That's 0.004 kilograms per meter. And I just do all that math out, and I can find the tension that I have to tune it to. Now, when I'm tuning a guitar, I'm not thinking newtons, 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 newtons. Nobody's thinking about the newtons. What I do is I tune the guitar until my ear tells me that it's an A note. Or I have a fun little electronic gizmo on the end of my guitar that tells me what the notes are. Obviously, there's a huge relationship between the music that we enjoy, the instruments that we created. The instruments create the vibration creates the sound stimulates the nerves in our brains in a pleasing way that we call music.